Welcome to chemistry classes. In this video, we are going to discuss about F block elements. In F block elements, we are going to discuss here lanthanides. General introduction about lanthanides. Also, we will discuss here lanthanide contraction. Lanthanide contraction, also its consequences. Okay, so here we will discuss general introduction about lanthanides, lanthanide contraction and its consequences. So see here F block elements, it consists of two series. You can see here F block elements. Here this F block elements, it consists of two series, lanthanoid series and actinoid series. Lanthanoid series, okay, lanthanoids and actinoids, these are the two series in F block elements, okay. And here lanthanoids which consist of 14 elements after lanthanum, 14 elements in lanthanoids. Similarly, in actinoids also consist of 14 elements. Okay, actinoids also consist of 14 elements after actinium. After actinium, actinoids. After lanthanum, lanthanoids. Okay, and here the most common oxidation state of lanthanoids are +3. The most stable oxidation state of lanthanides are +3 oxidation state. Okay. Also, when we move from left to right in lanthanides, its atomic and ionic size gradually decreases. Atomic and ionic size of lanthanides decreases from left to right. Okay. Also here lanthanides, they show similar chemical properties. Okay. And here actinoids they shows different oxidation state. Here we discuss lanthanides. Lanthanoids shows most stable oxidation state +3, but actinoids they shows different stable oxidation state. Okay, and also actinoids they shows different chemical properties. Lanthanides they shows similar chemical properties, but actinoids they shows different chemical properties. Also actinoids they shows radioactivity. Understand here more details about lanthanoids. We have to understand more details about lanthanoids. Lanthanoids, the general electronic configuration of lanthanoids is N-2F 1 to 14. Similarly here N-1 D0 to 1 NS2. The general electronic configuration of lanthanoids FDS. This is the general outer shell electronic configuration of lanthanoids. Okay, outer shell S orbital, penultimate shell, second outermost shell D orbital, anti-penultimate shell, third outermost shell F orbital. Okay, so this is the third outer shell orbitals, and here in S orbital there will be 2 electrons, and D orbital there will be 0 or 1 electron, and F orbital there will be 1 to 14 electron. This is the general electronic configuration. Okay, so lanthanoids, their outer shell, these are the 3 outer shell: S orbital outer shell, penultimate shell D orbital, anti-penultimate shell F orbital. Here last shell always 2 electron, and D orbital 0 electron or 1 electron. F orbital, it depends on 14 different elements: 1 2 3 4 5 6 7. Okay, then 8 9 till 14. You can see here this table. These are the different electronic configuration of lanthanoids. Okay, and also here this will be NS2. and here D will be n minus 1, and F will be n minus 2. For example, here 4s2, then it will be 4 minus 1, 3D, it will be 3D. Okay, and here it will be n minus 2. Okay, n is equal to here 4, then here it will be 3D, and here it will be 2F. Okay, so this is the general electronic configuration of F orbital. Clear? And here next one, we have to understand here oxidation state. We have to understand here oxidation state of lanthanoids. Oxidation state. The most stable oxidation state of lanthanoid +3 oxidation state. This is the most stable oxidation state of lanthanoids. We discussed before actinoids, they shows different stable oxidation state, but lanthanoids most stable oxidation state +3 oxidation state. Lanthanoids also shows +2 and +4 oxidation state in aqueous solution or in solid state. Okay, lanthanoids in solid state or in aqueous solution, they shows also +2 and +4 oxidation state, but most stable oxidation state, generally most stable oxidation state is +3 oxidation state. Clear? Also we have to understand here cerium and terbium shows +4 oxidation state. We discussed most stable oxidation state +3, but there is one exception case, cerium and terbium, it shows +4 oxidation state. Okay, look here, cerium, here xenon, after xenon 4f1, 5d1, 6s2. This is the electronic configuration of cerium. Okay, so here after losing 4 electron, here 2 electron, here 1 electron, here 1 electron. Okay, this is 1 electron. So cerium lose all these 4 electron and it will change to cerium +4. So cerium and terbium showing +4 oxidation state. Here 4f1, 5d1, 6s2. So after losing this xenon, after noble gas configuration, 4f0, 5d0, 6s0. Clear? Similarly, look here, terbium also showing +4 oxidation state. This is the electronic configuration of terbium, xenon, 4f9, 5d0, 6s2. So here 4f9, from here 2 electron will lose and here 2 electron will lose. After losing 4f9, after losing 2 electron, it will change to 4f7, 5d0, 6s0. We know fulfilled and completely filled electron, fulfilled and completely filled electronic configuration more stable. F14 and F7 most stable configuration. So here 4s7, 5d0, 6s2. So this is stable configuration. Also it is noble gas configuration. That's why cerium +4 and here it is terbium. Cerium +4 and here it is terbium. So this is also terbium. Okay, so cerium and terbium showing +4 oxidation state. Okay, so generally question asking why cerium showing +4 oxidation state. So you can explain this based on this electronic configuration. Okay, this is the electronic configuration of cerium. After losing 4 electron, it is noble gas configuration. Similarly, you can explain why terbium showing +4 oxidation state. Clear? Okay, so here we discuss here terbium and cerium showing only +4 oxidation state. Okay, here terbium and cerium showing only +4 oxidation state. Similarly, we have to understand here europium and ytterbium. Europium and ytterbium showing +2 oxidation state. Okay, these two elements showing most stable oxidation state, +2 oxidation state. See here, this also we can explain based on the subshell electronic configuration. This is the subshell electronic configuration of europium. Here xenon after 4f7 5d0 6s2. So after losing these two electron, it will change to 4f7 5d0 6s0. Okay, now it became europium plus 2 oxidation state, stable electronic configuration. Similarly here ytterbium, its electronic configuration xenon 4f14 5d0 6s2. Okay, 6s2. After losing these two electron, its electronic configuration xenon 4f14 5d0 6s0, and it formed plus 2 oxidation state. So here we discuss lanthanoids showing most stable electronic configuration plus 3 electronic configuration, but there are some exception case. Here terbium and cerium showing plus 4 oxidation state, reason we explained. Similarly here europium and ytterbium showing plus 2 oxidation state. This is the reason we can explain through here, we can explain with help of their subshell electronic configuration. Okay, also we have to understand here lanthanum and here gadolinium. Gd mean gadolinium and lutetium. These three elements, lanthanum, gadolinium, lutetium, these three elements shows only plus 3 oxidation state. So which three elements shows only plus 3 oxidation state? These three elements, lanthanum, gadolinium and lutetium. Okay, and here which element showing plus 4 stable oxidation state? Cerium and terbium. Which two elements showing stable plus 2 oxidation state? These two elements, europium and ytterbium. Okay. Okay, next one we have to discuss here lanthanide contraction. Lanthanide contraction. We know generally in a period when we move from left to right, atomic and ionic radius decreases. When you move from left to right in a period, atomic and ionic size decreases. Similar things we can observe in lanthanides. When you move from lanthanum to lutetium, their atomic and ionic radius decreases. We can observe a steady decrease in lanthanide when you move from left to right. Okay, and here the decreases of atomic and ionic radius in lanthanide, it is highly significant, and this process is called lanthanide contraction. When you move from left to right, when you move from lanthanum to lutetium, the atomic and ionic radius decreases gradually. We can observe a steady decrease in atomic and ionic radius, and this observation is called lanthanide contraction. Reason for lanthanide contraction. Next one we have to understand here reason for lanthanide contraction. Okay, so consider one element from lanthanides. Here these are the outer shell. This represent outer shell. Okay, and here this is outer shell, and this is penultimate shell, and this is anti-penultimate shell. Outer shell, penultimate shell, anti-penultimate shell. Okay, and here we discussed already before subshell electronic configuration of lanthanides. Here s orbital, d orbital, f orbital. This is outer shell, and this is second outermost shell, third outermost shell. In outer shell, in s orbital only 2 electron, d orbital 0 and 1, 0 or 1 electron, and most of the electrons are adding here f orbital. Electrons are progressively adding f orbital. Okay, and here d and s orbital there are few electrons, and most of the electrons are adding f orbital. And here we are talking reason for lanthanide contraction. Here this f orbital, this s orbital shows poor shielding. Okay, this s orbital shows poor shielding. Okay, that is the reason for lanthanide contraction. So here this f orbital shows poor shielding. That's why nucleus attract outer shell electron more effectively. Okay, so in all case, from left to right, in all case, same shielding effect, almost same shielding effect, because most of the electrons are in f orbital and this f orbital shows poor shielding. That is the reason for lanthanide contraction. Okay, that's why from left to right the atomic and ionic radius of lanthanides decrease. There will be a steady decrease in lanthanide from left to right. Okay, so remember poor shielding of f orbital. Okay, next one we have to discuss here consequence of lanthanide contraction. Consequence of lanthanide contraction. We discussed already d block elements. In d block elements there are three series: 3d series, 4d series, 5d series. We already discussed 4d series and 5d series. Atomic and ionic radius of 4d and 5d series are very close. Okay, they are almost same. They are almost the same. Atomic and ionic radius of third and fourth and fifth series of d block elements are almost the same. This is one of the consequence of lanthanide contraction. Okay, f orbital shows poor shielding. That's why their atomic and ionic radius shows a steady decrease, and fourth and fifth series of d block elements are their atomic and ionic radius are almost the same. Okay, and here another one, here similarity among lanthanides. Among lanthanoids, their atomic and ionic radius their atomic and ionic radius are almost very small difference. That's why lanthanides shows same chemical and same chemical properties. Okay, in lanthanides their atomic and ionic radius difference very small difference, almost the same. Okay, that's why they showing same chemical properties. Lanthanoids shows same chemical properties. That's why it is very hard to separate lanthanides from their mixture. Lanthanide mixture, you want to separate each lanthanides. Okay, it is very difficult because each members of lanthanides shows same chemical properties. What is the reason for same chemical properties? Their atomic ionic radius difference is very small difference. Atomic and ionic radius means atomic and ionic radius are very close each other. Okay, and here another consequence, basic property decreases from lanthanum to lutetium. In lanthanides their basic property decreases from lanthanum to lutetium. So lanthanum hydroxide shows most basic character and lutetium hydroxide shows least basic character. So basic character of lanthanides decreases from lanthanum to lutetium. Okay, and here we discuss lanthanides. They shows similar properties, similar chemical properties because their atomic ionic radius very close each other. Okay, that's why it is very hard to separate each lanthanide from the mixture. Okay, and here resemblance of second and third series. Second and third series of d block elements shows same atomic and ionic radius. This is also one of the consequences of lanthanide contraction. Okay, so these are the things we have to discuss in this video. Okay, so here in this video we discuss lanthanides, general introduction about f block elements. Then we discuss lanthanides, oxidation state of lanthanides, lanthanide contraction, consequence of lanthanide contraction. Okay, So you can check next video for further information. Okay, so thank you for watching this channel.